we're going to talk about fluid. We're going to discuss the continuity principle, and we're going to discuss Bernoulli's equation. Continuity, that is the volume of the fluid that flows fast at a point every second. That is known as the volume flow rate. Now it's important to note that it is measured in meters cubed per second. It depends on the velocity of the flow and the cross-sectional area of the pipe. As you see in the picture to the right, we have our equation for continuity, which is area of part 1 of the pipe times volume part 1 of the pipe, and that is equal to area of part 2 of the pipe times volume of part 2 of the pipe. So our continuity equation is one side of the pipe must always be equal to the other side of the pipe. Now, when we look at the pipe, if it is full, then whatever the volume of the fluid that enters the pipe must eject an equal volume of fluid from the other end. Well, now with that being said, the volume flow rate is equal at all points within an isolated stream of fluid. So whatever comes in must equal what comes out. So if we look at this conceptually, think about when you have a hose. And when you hold your finger as the water is flowing out of the hose and you hold it on to the actual part, the opening of the hose, and the water starts to shoot out faster. Right? So when the diameter of the pipe decreases, the velocity of the fluid stream increases, and vice versa. Now when we talk about these pipes and our flow, we have what we call as the mass flow rate. The mass flow rate is the substance which passes per unit of time. So how much mass of a substance passes per unit of time. As you see in our diagram here, we have an equation for the mass flow rate, and that is the density times area times volume. Now it is important to note that the unit for mass flow rate is going to be kilograms divided by seconds. Now, in all cases in this unit, we're going to assume we have laminar flow, right? And when we talk about laminar flow, we're going to talk about equal flow throughout the pipe. Now when a fluid is flowing through a closed channel such as a pipe or between two flat plates, either of the two types of flow may occur, depending on the velocity, the viscosity of the fluid. Laminar flow or turbulent flow can be seen. Laminar flow tends to occur at lower velocities below a threshold, at which it becomes turbulent. Turbulent flow is going to be where we have a flow that is traveling all around. It's traveling in different directions. It's having pressures in different directions. As you see here, our laminar flow travels straight across, almost linear and parallel to each other. A chaos theory. So let's think about this. A name given to a wide-ranging attempts to uncover the statistical regularity hidden in processes that otherwise appear random. Well, when we think about this, that we're talking about what's applied to diverse phenomena such as turbulence in fluids, weather patterns, motion and energy fields, predatory prey, cycles, the spread of disease, and even the onset of war. We have what's called the butterfly effect, right? This is where now we are working all the way up. We are now connecting it all to what we call, right? You affect one thing, you change one thing, all these other things will then change. Now moving on to Bernoulli's principle. This is where the velocity of a fluid is high, the pressure is low, and where the velocity is low, the pressure is high. We have that inverse relationship here. Some applications, if you look at the lift force of airplanes, right, we have that the pressure that is being exerted onto the plane, right, it's lower on the top, greater on the bottom, and that's what actually then helps the plane take off and lift off the actual ground. Another great example is when you talk about baseball and we're throwing a baseball, depending on the hand placement, the finger placement on the ball, and the wind and the pressure of the ball being thrown, the ball will move differently within the air. Another just example of Bernoulli's principle is prairie dog burrows. Think about it as air moves faster in lower pressure. So that's on the top of the land. Well, it's important to know that these burrows draw air through them, right? They have pressure and they draw air through them. Here you see Bernoulli's equation. We have the pressure of side 1 plus the density times little g times y1 plus 1/2 the density times the volume squared of object 1 equal to pressure 2 plus density times little g times y2 plus 1/2 the density times the volume squared of our second part. Often useful, right? So this is often useful when you have both a change in height and area. So as you see, we have a change in height. It comes in up here and travels down here. So when you have that change in height and area. Now, if there is no change in altitude, the equation just simplifies. It gets shorter because now we can take out our height, our y's. So that leaves us with P1 plus 1/2 PV1 squared, which is equal to P2 plus 1/2 rho V2 squared. Right, so it simplifies when we have no height. Alright, ladies and gentlemen, thank you for watching this mini lecture. Please get ready and start to begin your discussion code. Until next time, we'll see you later.